Hello and welcome to Intro to Proofs. If you're looking for something more specific, like a specific video on direct proofs, proofs by contradiction, proofs by cases, I'll have videos up for those as well. Before we begin, I'm just going to be assuming that you guys know some of the preliminaries here, so be sure to take a screenshot or just to Google them before you watch the rest of this video. So let's start off by defining the things that we want to talk about. A proposition is something that's either true or false, and we use the laws of propositional logic and the rules of inference on those. So remember, those things have to be true or false. So for example, all flowers are neon orange. That is a proposition because it's obviously false. And then something like, do your homework isn't a proposition because it's not true or false. It's just a command. So now let's talk about theorems, which are really big things in math. A theorem is something that we can definitively prove is true. So if we have a proposition that has a truth value of true, it is a theorem. And then when I say prove, I mean that we use a proof, which is something where we argue with logic and possibly with other theorems or things that we already know are true. So what are these things that we know are true? Well, some of them are axioms, which are statements that we just assume are true or that are kind of like self-evident to us. Cool, so let's talk about some of the types of theorems that we're going to be proving in the future. Some of these are universal statements, so something like the statement that I said before, all flowers are neon orange, except obviously that wouldn't be a theorem because we can't prove that it's true. So maybe an example of a theorem would be all living humans need to breathe. Other than universal statements, we also have existential statements, which are statements that are like, there is a thing or there's at least one thing that's this way. So if I say, at least one day during this week, I got out of bed before 7 a.m., that's an existential statement, and I can say that it is a theorem because it did happen. So how do we prove these specific different types of statements? For universal statements, we have two main ways, and the first way is proof by exhaustion. So if my statement was, every day of this week, I got out of bed, I could go through each of the days of the week exhaustively because there's only 7 of them, right? So it's not too much work to go through proof by exhaustion. The other kind of proof format that we have is universal generalization. So if I say that theorem that I said again earlier, every day this week I got out of bed, and I don't want to go through every single day saying like, oh, Monday I did that, Tuesday I did that, Wednesday I did that. I can say for any arbitrary day of the week, I got out of bed. So that generally works because we're assuming that like if we can choose any one of those random days, it's basically a representative of the entire set. So how do we prove existential statements? The first way is through a constructive proof of existence. So if I say something like, there was a day this week where I had chicken. All I need to do is find an example of that, right? All I need to do is say like, oh, on Tuesday I had chicken. And that's good enough for proving that it exists, right? The other kind of proof is a non-constructive proof of existence, which is usually a little bit harder, and it usually builds on axioms and or other theorems. So if you can kind of tell, constructive proofs of existence are almost like proofs by exhaustion, and universal generalization proofs are kind of like non-constructive proofs of evidence just in the way that we set them up. So that was all about proving different kinds of statements to be true. We can also disprove statements, right? So for universal statements, we usually disprove them by counterexample. So that's just like constructive proof of evidence, but we're finding a counterexample. So let's say I give that example that I gave all the way back in the past, all flowers are neon orange. Then all I need to do is find one single counterexample and that disproves it. So all I need to do is go outside and pick up a white flower or something. I say, oh, it's not neon orange. And then I've disproven the entire universal generalization. For existential statements, it's a little bit harder because then we need to do a universal generalization for the whole thing. The specific kinds of proofs that you'll look at in the future, direct proofs are really good for universal statements. Proofs by contrapositive are really easy for if-then statements. Proofs by contradiction are also good for if-then statements, and they can also be good for some universal statements. Proofs by cases are good for universal generalization statements, where you can kind of split the different kinds of things in your set into smaller categories. And then proofs by mathematical induction are good for universal generalization statements that are for all natural numbers. So in terms of a general proof sketch, you're always going to state the theorem that you're trying to prove, and then you can usually say how you're planning on proving it. So if I want to prove this by contradiction, I can start off my proof by saying, we seek to prove this statement using contradiction. And then another good rule of thumb is just to state all the definitions of the things that you're using in your problem and state the axioms, if there are any, that apply to this problem in particular. Then you just plug in your definitions, use some logic and some clever manipulations and arithmetic sometimes, and then you should come out with the conclusion that proves the statement. So for an example, let's prove a universal statement using just words. If my name is Maggie Sawying Lai, then I'm 19 right now. So that's a universal statement, right? Because I can say, for all people named Maggie Sawying Lai, they are 19 right now. And that's another good trick to do when you're writing proofs. If the original statement doesn't have any quantifiers in it, you should always be thinking in your head, or even writing explicitly on your paper, the exact theorem or statement in quantifiers. It just makes things easier to prove for yourself and for your reader. So for that example, I would just use proof by exhaustion, because the set that I'm trying to prove things about should be pretty small. I'm pretty sure I am the only person that has that name. So for an example of proving a universal generalization that isn't just words, let's give the example, if n is an even prime number, then the square root of n is less than 2. So we can think through all our even prime numbers, right? It's just 2. So once again, I would use proof by exhaustion because there's literally only one case. And then another 2 examples for universal generalization instead of proof by exhaustion. Once again, the first one is going to be just with words. Every grade ever given in Comp Sci/Math 2170 is less than or equal to 100%. So I would use universal generalization because it would be a really big pain to go through every single grade ever given in this class. So this is kind of an example of how you would see that proof by exhaustion is definitely not the way to go. So for an example of how I would prove this, I would just say, by looking at the syllabus, which are maybe the axioms that we're going by in this case, we can see that for any arbitrary grade in this class, a grade over 100% is never assigned. Let's do another example with actual numbers. So my statement is, every real number squared is positive. Once again, I would use universal generalization just because that's a whole lot of numbers and you're not ever going to be able to go through every single one of them. For our next big chunk of examples, let's prove some existential statements. And once again, we'll start off with the wordy one. So there is a person in Comp Sci/Math 2170 who ate today. We would use a constructive proof of evidence for this one because it's really easy to find a single person, right? For an example that's more mathy, we can say there exists a natural number whose square is itself. Once again, this is a pretty easy constructive proof of evidence because I can just say, oh look, 1 squared is 1 and they're equal. So I hope you guys can kind of see how constructive proofs of evidence are similarly structured to proofs by exhaustion, right? You just show each of those cases out and that's enough, logically proving it to be true. Let's look at some situations where we might use a non-constructive proof. So for our word one, it would be maybe, there is a person in Intro to Discrete Math who went to the bathroom today. So we could use a constructive proof of evidence for that one. I could just wait outside the Stanley Thomas bathroom for a while and wait for people to come, but that would be gross and I don't really want to do that, and I don't think anyone wants to do that either. So this is an example where we would use like an axiom of math, or in our case, human needs. I would just say, I know that humans need to go to the bathroom and that all the people in this class are human. Then everyone in this class has gone to the bathroom at some point during this day, and I've proved my statement. Let's also look at a more math one. This is using some continuity things, so it probably will have helped to take calculus before looking at this kind of proof. The statement is, there exists a real number such that x squared plus 2x minus 4 equals 0. We could use a non-constructive proof for this one again. You would just use a quadratic formula and take a look at it. But we could also use a non-constructive proof in this way. So we know that f of 0 is negative 4 because 0 squared plus 2 times 0 minus 4 is just negative 4. And that f of 2 is equal to 4. Once again, we just plugged 2 in and shoved it out. So the reason why I picked 2 is just because I knew that that would give me a positive number. So we know that f of x is a polynomial and it's continuous by some things that we learned in calculus or maybe analysis if you've taken that. So we can use the intermediate value theorem to say that there has to be some x in between 0 and 2 such that f of x equals 0. So hopefully you can see that this is a valid proof, but that, just like our last one with words, it builds on some previous knowledge that you have to have had, which are axioms or theorems. Finally, let's disprove some statements. Once again, theorems have to be things that we can prove to be true. So these statements that we're proving false are evidently not theorems. They're just propositions that we can prove to be false. Let's give another example that just has to do with words. If I live with Maggie right now, I'm related to her. So we're trying to disprove it, right? So in your mind, you can kind of say, what do I want to show then? So we're trying to show the opposite of that. So we really want to show, if I live with Maggie right now, I'm not necessarily related to her. So we can use proof by counterexample here, right? Because this is a universal generalization statement that we're proving by a counterexample. Let's also give a math example. So every prime number is odd. So once again, we should say what we're trying to prove then. We're trying to prove that not every single prime number is odd. And once again, we can use proof by counterexample because it's pretty easy to just say that 2 is even and it's also prime, and then we're done. Let's disprove some existential statements. Once again, we need to use universal generalization statements to disprove existential statements because that's kind of the reverse. So for our first example, there is a first-year student at Tulane that is 1,000 years old. So we want to show that out of all Tulane first years, none of them are 1,000 years old, right? Because if even a single one of them were, then our statement would be true. So we would just use universal generalization because this is a for-all statement now. And for our math example, let's say there is an even number whose square is odd. What do we want to show? So we want to show that all even numbers have even squares. And once again, we use universal generalization because this is a for-all statement now. Stay tuned for a more specific proof of that last statement in some of my videos on proofs by cases, proofs by contradiction, proofs by contrapositive, and direct proof. I'll link them in this video below. Thanks for watching.